Good morning or evening, depending on where you're tuning in from, and good afternoon to our viewers in Japan. On your screen, you can see the Falcon 9 rocket against the jet black canvas of the Florida night sky. I'm Michael Hammersley, a materials engineer in our avionics department, and I'm talking to you from outside mission control at SpaceX headquarters in Hawthorne, California, as we're getting ready for tonight's launch of JCSAT-16. We have a reasonably unobstructed view into mission control at the moment, which is a rarity. The small crowd developing behind me in anticipation of liftoff at 1:26 a.m. Eastern or 8:26 a.m. Coordinated Universal Time. You may recall that we launched JCSAT-14 a few months ago, and this mission tonight will have a fairly similar mission profile. It's also going to be a Geostationary Transfer Orbit. We'll be lifting off from Cape Canaveral, ascending to that GTO with a second stage burn, coast phase, and another second stage burn. And the first stage will be landing on the drone ship. One of the big differences will be attempting a single engine landing burn instead of a 3-engine landing burn. We hope to be bringing you good footage of that all night.
This is Tom Perderio. I'm a firmware engineer in the avionics department here at SpaceX. Now, for those of you who have never seen a Falcon 9 launch before, let me walk you through exactly what you're going to be seeing on the pad before the launch tonight. So first and foremost, the large structure in the center of the pad, that is the Falcon 9 rocket. The Falcon 9 rocket is broken up into 3 different sections, the bottom section being the first stage, which takes up about 80% of the height of the rocket. On top of that is the second stage, and then at the very top there is the payload, which is tonight the JCSAT-16 satellite going to geostationary orbit. However, you can't see the JCSAT satellite right now because it's encapsulated inside the payload fairing. Now, the fairing is that nose cone-shaped structure at the very top of the rocket, and what it does is it protects the satellite inside from the intense aerodynamic forces of the launch as the rocket ascends through the atmosphere. Now, right now the rocket's being held vertical by the transporter erector, or strongback tower right here. That's that structure that's just to the left of the rocket. It's connected to the top of the rocket via the umbilical, which has electrical connections and plumbing that keep the rocket connected to the pad in communication and also keep it topped off with fuel as we prepare for the launch. The rocket's also held down at the very bottom by gigantic hold-down clamps. These are massive steel clamps that grab onto the bottom of the rocket and actually hold it down until all 9 Merlin engines are ignited and confirmed to be operating nominally. We then release the rocket and it ascends through the atmosphere. Also in the pad are 4 lightning towers, which you can kind of see through the darkness of the pad right now. What these do is they just protect all the pad electronics and the rocket itself from the lightning strikes that can be very common during the Florida weather. There's also a hangar just around the corner over there that the rocket was assembled horizontally and then rolled out to the pad. Throughout the mission, you're also going to be seeing a mission countdown clock in the top right-hand corner of your screen. And then at the very bottom is a mission progress bar. Mission progress bar has different types of events that are going to happen all the way to the launch, so you can keep track of exactly what's going to be happening right all the way down until liftoff in just a few minutes right now.
Hi, I'm Kate Tice, a process improvement engineer here at SpaceX. This is the 8th Falcon 9 launch of this year, and on this flight we're launching JCSAT-16. It's a communication satellite that will serve as a backup to the existing fleet of SKY Perfect JSAT satellites. Falcon 9 will be sending it to Geostationary Transfer Orbit, which you may hear us refer to as GTO. As usual, we'll be taking you to Orbital Mechanics School later on in our webcast, so we'll talk more about the details of GTO then. Also on deck for tonight is a drone ship landing attempt of the first stage. The rocket's guidance coordinates are set for the drone ship called Of Course I Still Love You, which is currently holding position in the Atlantic Ocean a couple hundred miles off the coast of Florida. Due to the extreme velocities and heating that the first stage is subjected to upon re-entry from a GTO mission, the stage return can be tough. However, tonight we're channeling our inner Simone Biles and we're hoping to stick the landing. To date, we've had 3 successful drone ship landings as well as 2 successful land landings. The last time we carried a SKY Perfect JSAT payload was JCSAT-14 back in early May of this year. That was actually the very first time SpaceX successfully landed a GTO mission back on a drone ship. That vehicle is currently at our testing facility in McGregor, Texas. We fired it up 3 times for static tests in late July, and you can see it there on your screen now. Since it was exposed to such extreme conditions upon re-entry from the JCSAT-14 mission, it's now being utilized as our flown benchmark vehicle. This means that we'll perform numerous static fires on the vehicle to evaluate what kind of wear and tear the stage and its components experience from each round of testing. Gaining a better understanding of this is an important next step to our path to reusable rockets. which of course is what we are trying to do here at SpaceX. We're trying to develop a rapidly reusable rocket system, and an awesome step towards achieving that goal.
Hello, I'm John Isberger, Falcon 9 Principal Integration Engineer. I'm coming to you from my desk here at SpaceX headquarters in Hawthorne, California. I'll be bringing you status updates during the countdown as well as during the flight of Falcon 9 carrying JCSAT-16 into Geostationary Transfer Orbit. Now it's late in the evening here in California, early morning at Cape Canaveral, but again, employees are beginning to gather out in front of the Mission Control Center in preparation for another Falcon 9 launch. Now we're deep into the launch auto sequence, right now at T-minus 10 minutes and 37 seconds. Everything on the Falcon 9 continues to go well as we proceed through this launch auto sequence. We're deep into the propellant loading right now. Currently, we are loading liquid oxygen into the first and second stage of the Falcon 9. You can see the view on the camera, the gaseous oxygen boiling off from the ground systems along the transporter rector strongback. We also began loading fuel at T-minus 35 minutes. Currently, fuel is loaded on the second stage, and we're getting ready to wrap up fuel loading on the first stage. Propellant loading consisting of liquid oxygen will continue up until about the T-minus 2 minute point. Now we rolled out to the pad at T-minus 17 hours. That's fairly early for us. The schedule allowed us to do this. We can normally do it in about 4 hours before liftoff. But once we got to the pad, that allowed our customer, the JCSAT-16 crew, to be able to do their spacecraft functional checkouts at about T-minus 10 hours. The spacecraft team has completed those checks. At T-minus 30 minutes, they went to internal power. That pretty much completes their activities other than monitoring the spacecraft for the rest of the countdown. The Air Force range is ready to support with all the assets, and the weather continues to look good, both ground level and upper altitude winds, for an on-time launch in just over 9 minutes.
The Falcon 9 rocket is capable of launching payloads to many different types of orbits. Now, communication satellites typically go for geostationary orbits, and these are typically protected inside the fairing. You can actually see some shots of our JCSAT-16 fairing right now. Again, that fairing typically just protects the satellite, which you can see is not really designed to go through launch-level winds. Now tonight we're launching the JCSAT-16 satellite into a geostationary orbit. This is actually the second JCSAT satellite we're launching for SKY Perfect JSAT in 4 months. JSAT has 16 satellites in orbit, making it Asia's largest satellite operator. The satellite was built by SSL, which is based in Palo Alto, California, in the heart of Silicon Valley. They are one of the world's leading manufacturers of commercial satellites. In fact, they have more commercial geostationary satellites in orbit than any other satellite manufacturer. The satellites, of course, beam us television, but they also provide radio, broadband internet, and mobile communications. This will be the 4th SSL-built satellite to launch on a Falcon 9 rocket. The SSL has manufactured more than 250 satellites, beginning back in 1960 with the world's very first communication satellite, the Courier 1B. In addition to building satellites, SSL was also the exclusive provider of batteries to the International Space Station for more than 10 years. They also built deep space antennas for the twin Voyager spacecraft, and one of them is now in interstellar space, further than any man-made object ever. Now, we're not quite going as far as the Voyager spacecraft today, but we are going pretty far. 36,000 kilometers above the surface of the Earth is no joke. It takes a lot of effort, a lot of fuel to get up there. And when it gets up there, the JCSAT satellite will be orbiting in exactly the speed of the Earth's rotation. So you'll be able to look at it, point the satellite dish, and get all that radio, broadband internet, and mobile communication that's necessary. So the launch of the JCSAT satellite is coming up pretty soon, just a few more minutes.
Okay, so we're about T-minus 7 minutes until liftoff. As you can probably hear, the crowd is starting to grow here by Mission Control. As you've just seen, tonight's payload is JCSAT-16, a communication satellite built by SSL. We're launching it for SKY Perfect, which is Asia's largest satellite with a current fleet of 16 satellites. The one we're sending up tonight will serve as a backup to that existing fleet. In order to accommodate this need, it was designed with the flexibility to be used at multiple orbital slots, as you heard Tom talk about. The SKY Perfect JSAT family of satellites are commercial communication and television broadcasting satellites. These satellites serve Asia, Russia, Oceania, the Middle East, Pacific Islands, and North America with Ultra HD 4K television programming and mobile communications for the maritime and aviation industries. From Wi-Fi and movies on your next flight to high-def in-home television streaming, the JCSAT fleet has it covered. Also included, communication capabilities for boats and airplanes in the Pacific. Like we've been saying, we're sending it to Geosynchronous Transfer Orbit, also known as GTO, and that's about 36,000 kilometers away. But to put that in more relative terms, that's about 1/10 of the distance between Earth and the Moon. So we're going to be talking a little bit more about why we're sending it that far away, but essentially it has to deal with the fact that it's a communication satellite and it needs to remain over the same spot on Earth in order for those services to be delivered reliably. So we're going to talk more in a little bit. Let's follow along with the countdown.
So JCSAT-16 is a Geostationary Transfer Orbit mission, and that means we'll be attempting to land the first stage on our autonomous spaceport drone ship, Of Course I Still Love You, in the Atlantic. And there you've got a beautiful view of the drone ship trucking towards a holding location. The drone ship placement is defined almost entirely by whether or not the mission is to low Earth orbit or not. In a launch to low Earth orbit, we have enough propellant and performance in the first stage to do a boost back burn, which means we can come all the way back to land. With a GTO mission, though, we don't have a boost back burn, so the landing zone is dictated by the natural arc of the first stage booster after stage separation as it just continues further into the Atlantic. Once that location has been chosen, the orientation of the drone ship is defined entirely by waves and not by how the rocket is approaching. So I have this little pseudo model of the drone ship here, the orientation being how it's placed in the water. So if you've got waves and you've got the long edge of the drone ship facing the waves, the drone ship is actually going to rock a fair amount. Whereas if you have the short side facing the waves and the waves approaching, the vertical displacement is the same, but the angle is a lot lower, and that makes it easier for the rocket to land properly. The drone ship also stabilizes itself against those waves by taking on seawater as ballast and settling lower in the rocket, or lower in the water, forgive me. The drone ship doesn't actually speak to the rocket. Instead, it uses GPS and 4 powerful thrusters, one on each corner, to maintain its position, and the first stage aims for that same GPS coordinate. In the final few seconds, as the first stage approaches the drone ship and the landing burn begins, I can use either 3 engines or 1 engine for the landing burn. 3 engines uses less fuel, but it's a bit like slamming on the brakes at the last second. That's harder on the rocket, and you don't have very much time to correct because the engines are only burning for a short period of time. A 1-engine burn uses more fuel, but it's a softer landing, and you get more control. And that allows you to land in higher winds.
We're at T-minus 3.5 minutes and continuing to count down for an on-time launch at 26 minutes after the hour. Now we're deep into that launch automatic sequence where the ground computer and the Falcon 9 flight computers are in control of the countdown. The team of SpaceX engineers in the Launch Control Center at Cape Canaveral have minimal involvement right now. The computers are controlling the sequence. The engineers are watching over their monitors, ready to step in should something unexpected happen. We're also monitoring back here in Hawthorne, California in the Launch Support Center. Now we began propellant loading at T-minus 35 minutes after doing the standard poll of 13 people in the countdown to make sure we were ready to go into propellant load. We're currently loaded with fuel on the first and the second stage. We're going to wrap up liquid oxygen loading at T-minus 2 minutes. You can see right now on the monitor, the strongback is reclining away from the 70-meter tall Falcon 9. The strongback moves to a position of 77 degrees above horizontal, so it's slightly leaned away from the rocket in preparation for liftoff so the Falcon 9 can clear. Now we're working no issues on the Falcon 9. Spacecraft is on internal. They're working no issues. The range is ready to support. Weather continues to support, including the upper altitude winds, which are fairly light tonight. So all systems are looking good at T-minus 2 minutes and counting. Let's listen in to the last minutes of the countdown of Falcon 9 carrying JCSAT-16 to Geostationary Transfer Orbit.
M1D TVC ground supply, full pressure. M1D fuel bleed complete. Vehicles in self-align. Stage 1, Stage 2, cryohelium and ACS secured for flight. Stage sub ISO secured.
VC confirm F9 in startup.
Falcon 9's in startup. Stage 1, Stage 2, pressing for flight.
T-minus 30 seconds.
Ground helium closeout complete.
T-minus 20 seconds.
Falcon 9's configured for flight.
15. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off of the Falcon 9. Falcon 9 had cleared the towers.
You're looking at the Falcon 9 powering its way through the low atmosphere as it heads into the parking low Earth orbit. First stage continues to burn under the power of 9 Merlin 1D engines. We're already through the throttle down and throttle up phase. Coming up to transonic, let's listen in. Currently, Falcon 9 has gone through the supersonic speed transition, what we call going transonic. This is also the period of maximum dynamic pressure on the Falcon 9, where the loads on the vehicle, a combination of the density, the atmosphere at the lower altitudes, and the speed of the rocket, create the greatest loads on the Falcon 9. We've just heard the call in that MVAC-D chill-in looks good. We've begun passing liquid oxygen to the turbopump on the second stage engine, getting that turbopump cold as we get ready for ignition of the upper stage, coming at about T plus 2 minutes and 44 seconds. We're going to listen in. Major activities coming up now. At 2.5 minutes into flight will be main engine cutoff, followed by stage separation and upper stage engine ignition. Let's listen in.
This is the OSM. Stage separation.
You hear the cheering. The upper stage engine is lit, completing the sequence of shutdown of the first stage, separation from the first stage, ignition of the upper stage engine as we continue on into the low Earth orbit. That'll be the first of 2 orbits we're headed for tonight. The first somewhat circular low Earth orbit. Then after a coast period, we'll go into what is essentially a large egg-shaped orbit, the Geostationary Transfer Orbit, which will take the Falcon 9 with the JCSAT-16 spacecraft to an altitude of about 36,000 kilometers. You can see the upper stage nozzle. Here comes fairing separation.
Fairing separation confirmed.
And we have fairing separation. With that, let's talk to the team down on the floor.
And as the second stage is carrying the satellite now free of the fairing up to that low Earth orbit, or the beginning, that initial low Earth orbit before moving to GTO, the first stage is heading back towards the drone ship. Now, occasionally people think that a drone ship landing is harder than a land landing, and that's sort of true, but not for the reasons they think. A low Earth orbit mission, which can return to either land or the drone ship, is easier than a geostationary transfer orbit mission, which can land only on the drone ships. That's because a GTO mission requires a lot more speed than a low Earth orbit mission, and that means it requires more propellant. It even gets a little bit trickier than that, so we've got a nice animation to show you what's up. Here we have a picture of the Falcon 9. We zoom in on the first stage. It's got liquid oxygen propellant on top and RP1 kerosene fuel on bottom. And as it burns through each of those propellants, the thrust that's produced is more or less constant. But it's harder to move or harder to accelerate when it's heavier. Just like a pickup truck will accelerate slower when it's towing a lot behind it. So when you burn 20 seconds worth of fuel at the beginning of the flight, you've only added about 200 kilometers per hour to your speed. But 20 seconds worth of fuel when the rocket's almost empty, just before main engine cutoff, adds more than 2,000 kilometers per hour to your speed. So, sort of perversely, it's really the fact that we don't have much propellant left that allows us to reach the speeds required to reach GTO. And if you don't have much propellant left, of course, then you can't do a long re-entry burn to minimize the re-entry forces on the vehicle, and you get much less of the control that comes with a longer single-engine landing burn. So it's really the GTO landings that are hard, not necessarily whether the first stage is landing on a drone ship. So again, we are headed towards the drone ship on a GTO mission, so we don't get the boost back burn. We have a re-entry burn, but it's a bit shorter than what we're getting on some of our low Earth orbit missions. And we do manage to get a single engine landing burn, at least that's the attempt for this one, which means that we'll be able to have a longer control and longer descent, which is nicer because it's less forces on the rocket in that final descent. It can compensate for larger wind speeds, which is also pretty nice. So fingers crossed that's happening soon. Now, if you're interested in the math behind what's going on there in terms of the fuel and the speed, you can look up the Tsiolkovsky rocket equation, which explains a lot about how those two are related.
We're at T plus 6 minutes and 20 seconds. Things continue to go well for Falcon 9 carrying JCSAT-16 spacecraft into the low Earth orbit parking orbit. Looking at the upper stage engine, we've just heard the call out. Stage 1 entry burn has begun. This burn will last about 23 seconds. Let's listen for the completion of the burn.
Stage 1 entry shutdown.
And we've had shutdown of the first stage engine. That burn of 3 Merlin 1D restartable engines begins to slow down the first stage so that we can land on the drone ship out in the Atlantic Ocean. Meanwhile, the second stage continues to power and orbit. We're heading due east for that initial parking orbit. You can see the Merlin vacuum engine nozzle glowing white-red on the screen. That's normal. That's what we expect to see. Trajectory looks good. Power looks good. We're on course. Everything continues to go well at T plus 7.5 minutes. So let's turn it over to the team on the floor as we get ready for the landing burn of the first stage.
So as you've just seen, we have a lot of good stuff going on so far. Successful separation of our first and second stage. Second stage is carrying JCSAT-16 all the way out to Geostationary Transfer Orbit. Right now we're waiting for the third and final burn to begin, which of course is the landing burn.
So the landing burn is going to occur, and we actually should be able to see it as from the video that's currently on deck of the drone ship. Now this video hasn't historically been the most reliable. We hope to bring you as high quality video as possible, but there's no Wi-Fi out in the middle of the Atlantic Ocean. We are relying on a satellite link that is susceptible to the vibrations of the landing burn itself.
It's true. So when the rocket descends onto the drone ship, it starts to shake, and the satellite that's pointing up to communicate, or the satellite dish that's pointing up, Oh, we're just getting word that the landing burn's beginning. Focus your attention and we'll see if we can see it.
It looks like we could see the exhaust gases just in the top of the frame.
It's because those things have frozen, which, like we said, this speed, there's no Wi-Fi out in the Atlantic Ocean yet. So we can't bring you a status update, unfortunately. We would love to know as much as you.
We actually, back to the main mission briefly, we did just get a confirmation of a good orbit from the second stage. It's as excited as we all are to figure out what happened to that first stage. The primary mission today is to bring JCSAT-16 into geostationary orbit, and we're actually doing great on that front with our confirmation of good orbit.
So that good orbit is the initial stage. It's that initial low Earth orbit section before the second stage begins a second burn to turn that orbit from a circular...
Looks right, X marks the spot, right in the center of the drone ship. It's always great to see one of our boosters come back down to the surface of the Earth. Hopefully we'll get a chance to take a look at that thing and hopefully get it flying sometime soon.
Yeah, so that's, I guess, the completion of a secondary objective. It's important to remember that that primary mission is the satellite. And we're going to move into a coast phase shortly. About 17 minutes long, while the second stage moves into the correct position to begin a second burn. And that second burn will change the orbit from that circular low Earth orbit into a giant egg-shaped orbit, where the top of the orbit is at 36,000 kilometers, which is the geostationary distance.
Now, before we get it there, like we said before, it does take a bit of time. So we have about 16, 17 minute coast phase between basically until the next engine lights up again. We're actually going to be taking a break in a little bit. We hope that you stick with us. Of course, that's a great shot. Wow, that's awesome.
A fantastic shot.
But we hope you stick with us. We're going to be grabbing some coffee and wow, this is awesome.
We'll see you in 17 minutes after the coast to guide you through the second stage relight and hopefully a good separation.
Welcome back. John Insperker again from the Webcast headquarters here in Hawthorne, California. We're coming up in about 10 seconds for reignition of the upper stage engine. Let's listen in, see if we can pick up anything on the countdown net. And you can see we have ignition of the upper stage engine. Currently, second stage is over Africa. Data is coming back from the SpaceX ground stations in Africa, carrying the camera views from the second stage. We're going to be accelerating to about 4.5 Gs of acceleration. This will take us to the Geostationary Transfer Orbit. The burn itself lasts about 1 minute. That'll take us to about 36,000 kilometers, after which we finish the 1 minute burn. We'll shut down and then we'll check what the orbit is. Let's listen in for shutdown of the burn. We have shutdown of the upper stage engine. You may have heard the call out. We have a nominal geostationary transfer orbit insertion. The high point of the orbit, just over 36,000 kilometers. In the next several minutes, we'll be seeing spacecraft deployment from the second stage of the Falcon 9. And for that, let's turn our attention down to the team on the floor after a successful burn of the Falcon 9.
So as you just heard from John, we had a great second engine start as well as a cutoff, and at this point we're just waiting for the payload to deploy. Now in case if you have just joined us, it's early morning in Europe, so maybe you're just tuning in. Quick recap of the event so far this evening. We had a great liftoff of Falcon 9 carrying JCSAT-16. The two stages separated. The first stage came back down, and to our delight, appeared on the drone ship, Of Course I Still Love You, which of course is in the Atlantic Ocean right now. Now the second stage, as you can see, is continuing on. In fact, you can see planet Earth lit by the sun there in the background behind the second stage nozzle. And like I said before, right now we're just waiting for the payload to deploy.
Now, the payload, that JCSAT-16 satellite, is currently attached to the top of the second stage by means of some clamps and some springs. When we send the signal to separate the payload in just a few minutes, the clamps will release, and then the springs will give the JCSAT satellite a gentle push out into the great unknown, where it can then deploy its solar panels and make communication with its teams on the ground.
At the moment, both the second stage and the payload are ascending to the tip of that egg-shaped orbit at 36,000 kilometers. At that point, I guess once the satellite takes over control, and it's preparing to do that at the moment before it fully deploys, it uses its own onboard thrusters to circularize its orbit at 36,000 kilometers, which is that geostationary orbit.
Yeah, and like we said before, 36,000 kilometers, that's about 1/10 of the distance between Earth and the Moon. Now, there are some pretty cool technologies on board JCSAT-16. One that has been around for a while, actually, is something that we called an MLI, and that's known as a multi-layer insulator. And there on your screen, that's what you see as that gold reflective material, and it's quite simply multiple layers, typically metal-coated plastic layers, sometimes aluminum, and satellite makers, in this case SSL, use that to protect the instrumentation and the sensors on the satellite from the extreme heats that it incurs. So whenever you're in direct sunlight, it gets really hot, and whenever you don't have that sunlight, it can get really cold. So to protect the variation in these temperatures, an MLI is utilized.
Now, it turns out that keeping a spacecraft warm or cold isn't that different than when you want to get warmer at, say, a cold winter night, adding more blankets onto a bed. Multi-layer insulation is essentially just like hundreds of very, very tiny blankets all sandwiched together. And we've been using this to shield our spacecraft since the 60s. The Apollo lunar module had a lot of MLI on it. It's basically the same technology. And we use this to make sure that the electronics inside the spacecraft or satellite stay at exactly the right temperature so that it can stay up for decades at a time.
Yeah. And for maybe on-Earth application, for example, when I go backpacking and camping, I use MLI mentality. I put multiple layers of aluminum between me and the fire to make sure that I don't get too warm or I keep my food hot.
The big difference between space and Earth sort of aluminum usage in that is that in space there's no air to carry heat, and there's no conduction because there's nothing next to you. So those three ways to transfer heat, and I know, Tom, you and I have talked about these
Three ways,
before.
yes.
MLI is primarily aimed at radiation. And by reflecting, carefully controlling how much radiation gets reflected and retained, the temperature of the satellite is controlled much better.
These satellites stay up here for very long periods of time. You can get, I think JC Satellite is meant to be up there for 15 years or more. The electronics on board need to be heated and cooled. There are different types of technology we use to cool it, like radiators, and then we have electronic heaters onto the spacecraft to make sure that it doesn't get too cold during the long solar nights.
So we're about 15 seconds until payload deployed. The shot that you see on your screen now, that is the nozzle of the second stage engine, which of course is not, it's not lit at the moment. We have cut it off for the second time as we have reached this preferred elliptical space. So we should have a shot of JCSAT-16 in just a few seconds. In fact, there it is now, and we're just waiting for it to release.
So you're looking at a shot from a camera that's on top of the second stage of the Falcon 9 rocket, looking towards, and there it goes.
So there's our visual confirmation of a successful separation of JCSAT-16.
That about brings our mission to a close. It still remains to make sure that the satellite's operating properly, but once that gets fully spun up and moved into its orbit, then our part's totally over. So to recap, we had a successful on-time launch of the first stage and second stage altogether. The second stage continued on towards that low Earth orbit, coast phase, and then second burn, successfully deployed the payload as the first stage made it back to a successful landing on the drone ship from a geostationary transfer orbit, which is checking all the boxes.
At this point, we're about to conclude the webcast. We'd like to thank SKY Perfect JSAT Corporation, our customer. We'd like to thank the Air Force for allowing us to launch off of Cape Canaveral and the FAA. And most of all, thank you, the viewers, for tuning in on a Saturday night to watch us launch a rocket.
If you'd like to join us here at the SpaceX team, be sure to check out spacex.com/careers. Also, be sure to follow us on spacex.com, as well as Facebook, Twitter, and my personal favorite, our Instagram account. Also, finally, we'd like to dedicate this webcast to Kenny Baker. May he rest in peace, as he was the man that brought life to our favorite droid, R2-D2.